Okay, let's continue with the same single phase half wave converter. See something more about the flow of power. So I am redrawing the diagram. This is the voltage across the resistance, across the inductance. This is the current. This is the input voltage. The output voltage is like this: output current, voltage across the resistance, voltage across the inductance. These are the things we have seen in the previous lecture. Let us say this is the angle theta when the current becomes maximum. Now, from alpha to theta, during this period, your input voltage is positive and the current is also like this, positive. Output current is also positive. It means the source is feeding the power to the load, that is input voltage into the current, that is positive. Source is feeding power to the load. What about the resistance voltage? From alpha to theta, the resistance voltage is positive. Current through the resistance is positive. It means the resistance is consuming the power. It is VR into I naught, or you can say I naught square R. From alpha to theta, inductor voltage is also positive and the inductor current is also positive. It means the inductor is storing the energy in its magnetic field, and that power input to the inductor is VL into IL. This is also positive. So what happens from alpha to theta? This is feeding power to the load. Source, the resistance is consuming the power as I square R. Inductor is storing the energy in its magnetic field. Now consider theta to pi. From theta to pi, input voltage is positive, current is positive, means source is still feeding the power. From theta to pi, resistance voltage is positive and the current through resistance is also positive. So the resistance is still consuming the power VR into I naught, that is I square R. No change. But from theta to pi, inductor voltage is negative, but the current is positive. It means now the inductor is releasing the energy, stored energy. So what happens? Source is feeding power to the rest of the load. Inductor is also releasing its energy, and that entire power is going to the resistance, which is consumed by the resistance I square R. This is the output power. Now consider from pi to beta. From pi to beta, Input voltage is now negative, but the current is positive. So instead of feeding the power, now this voltage is, now the power is negative. It means source is getting power back. VR voltage is positive. Current through resistance is always positive, and therefore the resistance is still consuming the power. Inductor voltage is negative. Current through inductor is positive. It means the inductor is releasing its stored energy. So what happens? Now inductor is releasing its rest of the stored energy. Part of the energy is consumed by the resistance as I square R, and rest of the energy is going back to the source. This concept is very much required if you want to understand the effect of freewheeling diode. Later on we'll discuss. But once again I repeat, from alpha to theta, source voltage is positive, source current is positive, source is feeding power to the rest of the load. Resistance voltage is positive, resistance current is positive, resistance is consuming the power. Inductor voltage is positive, inductor current is positive, inductor is storing the energy in its magnetic field. From theta to pi, source voltage is positive, current is positive, source is still feeding power to the rest of the circuit. Resistance voltage is positive, resistance current is positive, resistance is consuming power. But inductor voltage is negative, current is positive, means now inductor is releasing the energy. So energy released by the inductor goes to the resistance, power coming from this source, that is also going to the resistance. And from pi to beta, input voltage negative, current positive, source is getting power back. From where the power is coming? Inductor is releasing its energy, because this is negative, this is positive. Inductor releases the energy. Part of that goes to the resistance, rest goes to the source. And in this way, the power flow takes place. Whatever energy inductor stores, same energy it releases, and that's why on an average under steady state there is no power input to this inductor, and that's why we say the inductor average output voltage is 0. Under transient condition, yes, it will not be 0, but once it has reached in a steady state, then it is basically 0. This is how we can analyze single phase half wave. Rest all converter circuits, they are analyzed exactly in the same manner. Let's consider one or two more cases of the different nature of the load. Say for example, now load is having a resistance and a DC source. How to analyze? When it is replaced by a switch, anode voltage will be same as the input voltage. And the cathode voltage will be same as VC voltage once it is replaced by a switch and the switch is open. No current flow, no drop across this, so voltage of this point with respect to the reference point will be same as VC. And now the difference of the two voltages will give you the voltage across device. So the difference of this voltage and this means this is the positive voltage and rest is the negative. So thyristor becomes forward bias from this point to this point. But firing angle is always measured from here. Let us say this angle is theta. So root 2V sine of theta, that is equal to VC. Theta is sine inverse VC upon root 2V. Till theta, thyristor is reverse bias. But you can trigger it once it is forward bias by giving a short duration pulse at an angle alpha. Before you trigger the device is off, so the output voltage will be same as VC. And once the device is turned on, input voltage appears across the load and that becomes VC. That becomes this. How long conduction will be there? That depends on the current. So during conduction, input voltage appears across the load so the output current is the output voltage or minus VC divided by R, or you can say it is input voltage minus VC divided by R. Input voltage minus VC means this vertical distance is the voltage appearing across resistance divided by R. At this point, input voltage is equal to VC, so the current becomes 0. You can see that now the current is become 0 somewhere here, which is less than pi. Current is 0 here, current becomes 0 after this. So till this point conduction is there. After that the conduction stops, output voltage will be same as VC. If you want to find out the average output voltage, it is 1 upon 2 pi from 0 to alpha, it is same as VC. From alpha to beta, it is same as input voltage. And from beta to 2 pi, it is again same as VC. do it mechanically because area under the curve divided by the 2 pi, that is the average output voltage. You can modify this equation, this expression like this: 1 upon 2 pi 0 to alpha Vc d omega t, alpha to beta root 2 v sin omega t, modifying it minus Vc d omega t. So I have subtracted one term, I should add the same term, no change. This term I have modified, and the third term is beta to 2 pi Vc d omega t. This and this, 0 to alpha, alpha to beta, beta to 2 pi, it is as good as 0 to 2 pi Vc d omega t. And the other one is alpha to beta root 2 v sin of omega t minus Vc d omega t. Vc into 2 pi gets cancelled with 2 pi, so it is Vc, and the other term is 1 upon 2 pi alpha to beta root 2 v sin of omega t minus Vc d omega t. You can simplify, you can find out beta will be same as, just like theta, you can also find out beta. Beta in this case will be pi minus beta. You can find out the average voltage. But why I am putting it in this form, there is a reason. If you look at the circuit, output voltage is equal to the voltage across resistance plus the DC voltage. It means average output voltage is average voltage across resistance plus the DC voltage. Average output voltage is Vc plus this particular thing. It means this term is the average voltage across resistance. Root 2v sin omega t minus Vc. Input minus Vc, that is the instantaneous voltage across resistance. From alpha to beta you integrate, divided by 2 pi, it is the average voltage across the resistance. And average voltage across resistance is always given by average current into resistance. So you can find out the average current. In this case you can notice average current is average voltage across resistance divided by R. It is not the average voltage divided by R. Now you can see the difference. In previous cases, when DC source was not present, we were getting the average voltage across the average output voltage divided by resistance as average current. But the correct is average voltage across resistance divided by R, that is the average current. In this particular case, one more modification can be done if we say inductance is also present. So R, L and VC all are present. This is the input voltage. And this is the voltage VC. Like previous case, we can say yes, beyond this point it will be forward bias, and therefore we can trigger it somewhere here by giving a pulse. And therefore till this point the voltage will be same as VC. Then it follows the input voltage, but now the load is having R and L and VC all. So what happens to the current? Again, you cannot find out the current expression in one go. You can say the current will have two components, steady state plus the transient. First, the steady state component. There are two sources, one is AC source, another is DC source. You can apply superposition theorem. So first you consider the AC source, the current is and another is due to DC source. Due to AC source, it will be same as root 2 V by Z sine of omega t minus phi. If you consider the DC source alone, the current will be in this direction, but in the assumed direction, if I say the assumed direction is this, because I have used plus sign, this current will be steady state current, remember. Simple RL circuit and you have a source VC. So VC by R current will flow in this direction, or in this direction it will be minus VC by R. So the total steady state current is this. And the transient current we do not know. We can only say at the instant of triggering this transient current is maximum. Sum of these two is the total current. And because of the inductance, the initial value of the current will be 0. So at omega t dash 0, that is at omega t equals to alpha, the current is 0. Put the initial condition here. using this value, from here you will get the constant A, put it in the expression. One term will be similar to the previous case, and the second term will be because of the DC source. You can see that how simple it is to find out the current expression if you follow this principle. Otherwise, you will have to write down a differential equation, take the Laplace transform, take the inverse Laplace transform, and then only you can find out the current expression. This is how you can get the current. And then current waveform, if you draw, it may become zero beyond this, some maybe here, maybe here, maybe here. It all depends on inductance. And as long as conduction is going on, output is same as input. And when the current becomes zero, this is the angle beta. This beta angle you can find out from the current expression by putting omega t equals to beta and equating this to 0. Solving it by hit and trial method, you can get the value of beta, and then you can find out rest of the things. This is how you can analyze this single phase half wave converter. We'll see more configurations in the next class.